All right. Hi, my name is Paco, and this is the Anyscale Academy webinar about Ray core features. We'll be talking about design patterns for parallelism in Python and also about profiling methods in Python to help you understand those trade-offs, understand the overhead that's involved in making those trade-offs, as well as where are the trouble spots that you want to parallelize. And I'll go ahead and get started here. We have, by the way, we have a Q&A feature on Zoom if you haven't used that before. So if you have questions, it really helps out to use the Q&A feature. That way it'll go into a queue that we can moderate and collect. I like to get questions while we're going through the material. We have plenty of time today, although I will be going full screen for part of this, so I won't be able to see the questions. I take that back. You know what? Actually, I will be able to see the questions. So I'll try to monitor chat on a second window, come to think of it. What I'm going to do today is provide some material in slides. The slides are in the repo. And we'll cover some background material. And hopefully, as you dig into the code, you'll start to recognize why some of the background material could become important for you, useful for you later on. And then we've got another section that's more hands-on coding. There's a series of notebooks that show the design patterns in code examples, hopefully code examples that you can reuse. They're a bit more refined than, say, what's in the docs for Ray. And then I have another segment that's added about profiling tools. And so we'll dig into that with an example with remote functions. And then closing, we'll have time for Q&A also, just to wrap up, and also some other resources that I'll recommend. So I'll kind of split it into those 3-4 parts. While people are coming in, let me open it up. If there's any questions to start out with while we're getting set up, please do. And I'll monitor on this other screen here. Great. And also we'll have a survey. Just want to get some feedback about the material, but also what are your interests in using Ray? And if you want to provide any feedback toward steering Ray toward particular use cases, it's a great place to do that. We'll send that out during the middle of the webinar. All right, Q&A. Parallelizing. Okay, great question from Rajesh. Will the learning for parallelizing also apply to RLlib? That's a really good point. Actually, a lot of what we're talking about and exploring today, these are already the underpinnings for what's used to build RLlib. That said, RLlib is about reinforcement learning, generally speaking, taking in some type of environment, and that environment could come from a number of different means, but one of the popular ones is to use an OpenAI gem. So if you're building simulation code in gem or in other methods, that in itself may need some parallelizing. So the learning methods in RLlib are already optimized using these components, but the simulation code that you use when you're running RLlib, that's something you may want to analyze further and see where there are patterns for perhaps parallelizing it. So that's a really good question. And also, I haven't seen that question come up very much. All righty. Well, let me just add for anybody who's joined, there's a GitHub repo, Ray tutorial. It's pasted in the comments, but I'll just make sure in case the chat buffer doesn't extend to anybody who's joining. Clone this repo, and there are instructions in the README. Just need to install pip install or conda install for the dependencies, and then run Jupyter Lab to get the notebooks. Okay, great. Oh, sorry. Okay, great. No problem. I saw the other chat. Great. All righty. Let me start up with the slides then. Oh, by the way, as I'm getting this going, I'll just mention part of what I'm going to try to show a little bit later when we're doing the notebooks is a bit of a compare and contrast. I'm going to be running off my Mac laptop, just in general, but then I'm going to cut over and show part of the profiling parts also running on my other laptop, which is a K-Focus box. It's an Ubuntu laptop with GPU built in. So it's a lot. It's very interesting to do distributed processing on that box. Basically, it's like a laptop version of GPU instances in the cloud that I would run to do machine learning work. And instead, I can actually attach it to Zoom here. So we'll take a look at it and sort of compare and contrast a 4-core Mac PowerBook Pro versus an Ubuntu running GeForce GPUs. Alrighty, I will start with some slides. Okay, great. And let me just confirm. Great. All right. Okay, a little bit of background about me, just real quick. I've done a lot of work in machine learning, also distributed systems. I did a lot of work early on in AWS with Hadoop and Spark and whatnot, and kind of made the odd mistake of studying AI and then doing a deep dive into neural networks for several years. Back at a time when it was pretty early and people were saying there was a waste of time. So anyway, the world has come back around. These days, I do a lot of work with graph-based methods, natural language understanding based off of GraphML. So I'm involved in some open source projects along those lines, KGLab and PyTextRank. But today's webinar is about Ray Core and the features in Ray Core. Just in general, there's an excellent overview from Ray Summit last year. And this is where Robert Nishihara, who's CTO of Anyscale, co-founder. He presented a really good survey of the landscape, the ecosystem for Ray and all that's going on. And now, of course, Ray is part of the underpinnings for optimizing in PyTorch and Dask and Spacey, Hugging Face, on and on and on. There's a lot in Ray. We're going to focus on the core parts, which provide foundations for these other bits. So you can think of the core parts of Ray as being a kind of pattern language. And just to pull back a bit, if you haven't seen this term pattern language before, it's used a lot in JVM and Java, especially. You talk about the Gang of Four book and the sort of design patterns that showed up for web apps that were popularized in the early aughts. There's been a lot of discussion about pattern language over there. Really, the term is borrowed from architecture. It was something that Chris Alexander did in Oregon State, had a bit of a political crisis just a couple weeks after Kent State tragedy. And Oregon State wanted to redesign part of their campus where there were some serious risks. They brought in a Berkeley professor in architecture who came up with this idea of a pattern language. And his name is Chris Alexander, and the original book was called A Pattern Language. It's a really good read, particularly if you're interested in some of the larger issues, big picture issues for software architecture. So coming back to Ray, there is a pattern language that has been used at Berkeley EECS department over the years, and that's some of the guiding material for what's gone into the development of Ray, since Ray is coming out of Rise Lab. And so, it provides really a lot of the details are written in C++, but there's API in Python, very simple to use in Python. We'll be covering that today. There's a newer version of bindings in Java, and then there are also public bindings coming up in C++. The kinds of patterns that we'll be talking about we'll cover these a few times, but the particular design patterns that we're talking about are task parallel, remote object, actor pattern, parallel iterators, etc. And these are not unique to Ray. These are something that are discussed broadly in terms of distributed systems. So, we're trying to develop here more of a lingua franca and be able to show you, where these kinds of things would come into play in different applications, regardless of what vertical you're working in, regardless of what you're necessarily trying to implement. Also, somewhat independent of the language as well. Although we'll be focused on Python today. The big takeaway is that this is a kind of toolkit, and within a given application, you'll probably need to mix and match. You'll probably use, more than one of these patterns to be able to parallelize what a particular application needs. And more, a lot of this notion is, I would say, moving away from applications and moving more toward pipelines. And how do we think about pipelines, particularly when it comes to data science, machine learning, AI applications? You're more and more, we're thinking about constructing pipelines and workflows than we are about, say, deploying a web app. But again, this material here is not specific to machine learning. It can be used for a broad range of applications. In Python, the way that Ray implements a lot of these kind of distributed patterns, it involves, on the one hand, use of decorators and closures in Python. And there's an article that I've got listed here, closures and decorators in Python. That has to do with PEP 318. It's also using the async IO library, so making use of futures, and we'll go into this in a bit. There's a few other resources. Definitely there's the patterns.eecs.berkeley.edu, and we'll cover different parts of this coming up here. I'll show it specifically for the different cases considered. But there's also a work in progress, a sort of community document called Ray Design Patterns. It's a Google Doc. A lot of people are in there editing. You might want to check it out. It's got more advanced material, more advanced discussions. So you can think of what we're covering today as kind of prereqs for it. But there's some really interesting material there, and you're very welcome to jump in and get involved in that. All right. So the first kind of pattern, and again, we'll be covering this a few times. So this is sort of the quick lecture version of introduction, and then we'll cover it up with more detail with programming examples later. So the first one is called task parallel. And this is something that's very familiar in big data. This is the kind of, this is the basis for things like Hadoop or other flavors of MapReduce, if you will. Certainly it relies on properties of data independence. So if you can take a data set and you have some type of processing that must be applied to a data set, and the different chunks, the different units of work can be run completely independently, then you can parallelize them. That's sometimes called embarrassingly parallel. And the two key points there are that it has the property of data independence between the different chunks. And also the processing is stateless. So if you lose a server, you lose a partition, you can just redo it, no problem. That was kind of the idea of Hadoop. So this is called task parallelism, and there are a couple of links here. There is the, let me see if I can dig this up. Okay, here's task parallelism in the Berkeley EECS design patterns for distributed systems. And it's a little bit more discussion about typical kinds of things you see here. I'll leave that for background reading. There's also something related called task graph, which is, say, if you can take a workflow or an application and break it down into different units of processing, which within each stage has its own properties of data independence and statelessness for the different chunks. But then you can build up the whole thing back into a directed acyclic graph. That's sometimes called task graph. And that's the kind of thing that you're going to see, again, in like Spark applications. It's very central to it. realistically, almost every SQL engine that I've ever heard of uses this to build up an internal query graph. It's also the kind of thing that's happening inside of a spreadsheet. If you take a look at what's going on there in terms of its dependency graph. So task parallelism and task graph, two very interesting concepts that show up quite often. Some of the background material on this, you can look at Mattson et al. From 2004, Patterns for Parallel Programming. That's a recommended one. In Ray, the way to do task parallel is real straightforward. If you have a function, a regular Python function, then you just add a decorator before it that says @ray.remote. And then when you call it, it's slightly different. So as you can see here, we've got my underscore function. It returns a value, an integer value. And to turn it into a remote function, a task, then we just add the decorator. And then when we go to call it, we'll say my function dot remote. So we use a remote method that returns back what is called an object ref in Ray, although in Python, you would probably hear this called a future. So that creates a task somewhere out on our cluster, wherever or whatever that is. Some worker process out in the cluster will manage it. And when I say cluster, I'm using that term very generally. The cluster may just refer to Ray running on your laptop on multiple cores. But think of it as a cluster. Think of it that we've got a future out to some task, some work that's going to be performed out by a worker. So we get this object ref back, and you can see it printed out. It's a big long hex string for defining that future. Then when we want to perform the work and get the result back, we call ray.get with that object ref, and that will return the value that's computed. So this is a way that we can take a whole bunch of small chunks, farm them out across the cluster, and then pull back in the results. Implementing MapReduce, at least the map phase of reduce with that should be trivial. There are some other resources I'll point to. There's an earlier tutorial for Ray that had some notebooks out on Google Collaboratory. So if you want to try those, it's interesting. Also, there's some more extended work on this out of the Anyscale Academy GitHub repo. And we'll be looking at a version of that particular example, Ray tasks. We'll be looking at that one a little bit later on. Okay, the next one up is called an object store, a distributed object store. In Ray, they refer to this as remote objects. This has to do with essentially shared memory. You can think of having a whole bunch of memory out across the cluster. You don't know exactly what server a given object lives on. You just know that you have this one global way to be able to access it. So we can put an object into the store, and then we can get its value back from anywhere in the cluster. And it will be unique. Roughly speaking, this is not far off the mark from what you would do with Redis. And in fact, if you look, there's usage of Redis. But basically, there's some type of object that lives somewhere out in the cluster. And I added as a reference, there's the shared memory page on Wikipedia. And this goes into some detail. If you read the original Spark paper, one of the really big points out of the conclusion of the original Spark paper was about distributed shared memory. And so that's a lot of what this is building. And the object store here is, it's real simple to use. Say we've got some object Y, then we say ray put of the object Y, we get back an object ref again. And then anytime we want to be able to access that from storage, we've got ray get object ref, just like we did before. That'll return the value. Note that these objects are immutable. Once you put them into the object store, you don't change them. But this gives us a consistent way of being able to get back objects, whether it's from a task that's being computed or whether it's from some shared memory, some storage. So you can think of that as like means for caching results, if you will. There's an item on Q&A. Let me see if I can take a look at it. All right, Anonymous is asking, will the presentation be shared as it has several references with hyperlinks and will be useful to navigate? Yes, absolutely. So the slides that I'm going through right now, they're part of the repo that we're going to be working with. There's a PDF version of this. And yes, very much to the point. There's a lot of links here. There's a lot of background material. If you want to study it in detail after the webinar, certainly. So all of that is uploaded on the GitHub repo. Good question. Let me dismiss that. Okay. Yeah, it's not dismissing. There we go. The next pattern that I want to cover is something you probably run into a lot. This is called actor pattern, and probably heard of this. This is something that's been really kind of came to the fore in the mid-aughts, but it's become very, very useful, especially in distributed systems for big data. So, this is part of what's under the hood for Akka and for Spark and Kafka and other things like that. The idea is very simple. It's very, very much akin to what we did with remote functions. With remote functions, remember, we take a function in Python and add a decorator. With actors, instead, what we do is take a class in Python and add the same decorator. And so at ray.remote. The difference here is that with actors, now we're talking more about message passing semantics. The different actors that are living out on the cluster, Ray will keep them running somewhere, and then they share messages. They pass messages back and forth. So effectively, each actor is maintaining some state, and then they're sending messages to each other about that state. Again, these live somewhere on the cluster, and I'm using the phrase cluster broadly. You don't know exactly where they're supposed to be living when you launch them. Ray takes care of that for you. But the big difference, of course, again, is remote functions are stateless, and actors, remote classes, are stateful. There's a original article about this if you want to dig into it from Hewitt et al. Going back to 1973. And this was in IJCAI, Universal Modular Actor Formalism for Artificial Intelligence. Okay, now this is something I like a whole lot because working with actors in JVM languages, well, in Java, it was a bit of code. It was a little trickier. It was really something, I would probably prefer to do in Scala. And then working with Python makes it even simpler here. So let's say we've got a class counter, and realistically, it doesn't need to say class counter object. We can get rid of the object part, but we've got a class, and we just add a decorator to its definition, ray remote. We're showing there that we've got a constructor and it's maintaining some state, some value. And then we have another class method called increment, which will just bump that value by 1. So the usage for this is very similar to what we saw before with remote functions. With actors, instead, what you do is you initialize the object, you say counter dot remote, and that will return back an object ref to that actor. That will return back the actor itself, right? The handle to the actor. Then what you do is you use that to call a method. So for instance, you would say counter.increment.remote, and that returns back an object ref. And then call rayGet on that object ref to get the value. So there's a couple of steps in there, but this allows us to be able to distribute state across the cluster. And that's very important, particularly given the kind of guarantees that it has on its message processing. There are a few other tutorials about this. If you want, again, there's one of the collaboratory notebooks from an earlier tutorial on Ray Project proper. And then there's also Dean Wampler did a really fantastic simulation. Excuse me. If you've ever used Conway's Game of Life, Dean Wampler rewrote that using Ray actors. It's a really interesting usage of them. One of the better presentations of life that I've seen, particularly because it has color coding for the lifespan. Basically, the different objects in the game are color coded based on how long they've been around. So it gives you this really dynamic view of what's changing in the game. So definitely recommend that. Another area is in Python, there's something called multiprocessing pool. So just kind of peeling back a bit, if you've been working with Python for any length of time prior to Ray and other forms of distributed processing in Python, yeah, parallel processing in Python over the years has had a very storied history. There have been a few different ways to approach this. Certainly there are things like greenlets and different views of threading or things that kind of appear to sort of be threading. So there's different ways of having this be event driven or using a queue or whatever. But one of the libraries that's available in Python is called multiprocessing pool. And so multiprocessing is the library, and then there's a pool object. And this has been built into a number of different applications that certainly I've used over the years. So it's out there. And what Ray provides is distributed multiprocessing pool. So using actors, they've rewritten a different version of this object. And using Ray, now you can distribute it and get much better throughput. But it's a drop-in replacement. It looks just exactly like the API for the one that's in Python proper. So to use this, it's very simple. You just import Ray util multiprocessing, and then you've got the pool object. So let's say we've got some sort of function f, and it's going to do a very simple mapping. It's just an identity mapping. We're going to give it a range. Basically, what we do is we call pool.map, and we apply the function to an iterator for the input. So that's really interesting because that's kind of the basis for what's called applicative systems. You'll probably hear this term used where you've got some kind of function, basically a closure, and then you can apply it to some collection of data. That's really useful in a lot of different cases. It's sort of the basis for things like Spark. So if you have applications that use multiprocessing pool already, this is a drop-in replacement. All right, and I have a question. Michael Siegel, tutorials call for NumPy 1.2. Downloading got an error, but I have a previous release, 1.14. Yes, definitely. That should be okay. And in fact, I was using an earlier version of NumPy just up until a couple days ago, but I did see some bumps come out from GitHub announcements. That's interesting. I'd love to see the error. If you want to drop that into an issue, please, on the Ray tutorial repo. We'll try to resolve that, and we may just need to roll back to an earlier version of NumPy. Thank you very much, Michael. I really appreciate that. Okay. And if rolling back to NumPy 1.14, if that doesn't work, let me know. But as best as I've seen off the cuff, thinking aloud, that shouldn't be a problem. If it is, we certainly need to troubleshoot. Okay, thank you. Another type of design pattern that we'll cover here, we've got an example coming up. Hopefully we'll show this in much more detail, but it's called joblib, and it's part of the backend for running scikit-learn. So this is built into scikit-learn. There is a separate repo called joblib, and I believe that scikit-learn is not the only thing that uses it. Basically, there's a drop-in replacement in Ray for running joblib, much the same as what we saw with pool here recently, or the same kind of idea that this is something that's existing in a lot of applications, so we can just go in and add it. I'll show a more extended example of something that's basically a little bit of AutoML-ish with a pipeline in scikit-learn coming up. Great question. Hi, Louis. Can Ray be used to parallelize network X? And if not, can you walk us through high level of how you go about making a library parallelizable with Ray? Fantastic question. Wow, and that one hits on several levels. Let me get a little deeper into the slides, and I'm going to cover that in a bit. But it's a great question about some of these libraries in Python. NetworkX, of course, is used for graph. A lot of graph algorithms are implemented on either NetworkX or iGraph. And from a high level, yes, there are ways, but it has to do, it's a little bit non-intuitive, and we'll cover that in a bit here. And also, we're both involved on a project that may be making use of that soon. So great question. All right, so using joblib, we'll go through this in a much more extended example. This is just a quick overview to kind of give you a flavor. But the idea is that if you have some kind of problem in a pipeline in scikit-learn, then you can just do a drop-in replacement there. It's like really just one line different, or actually a couple, 2-3 lines, to be fair. Let me keep me honest. But you register Ray, and then you just call what you would be doing in scikit-learn. In this case, we're trying to fit some hyperparameters in the space. One other pattern, one last one that we'll cover, has to do with parallel iterators. And I want to spend a little bit more attention on this one, talking about it from a higher level before we jump into the code about it. So parallel iterators are super interesting. Of course, throughout Python, there's all this use of iterators and a lot of really great reasons for doing that. It's sort of the Pythonic pep-ish way of doing things, working with list comprehensions and dictionary comprehensions, etc. Doing applies. This comes in really handy for some of the popular data science libraries like pandas, scikit-learn, and others. It comes in especially handy because it has implications for things like Dask. So if you have a lot of data too big really to run on one core, or at least you don't want to run it serially on one core, or maybe there's too much memory that's required, you need to farm it out across multiple cores, multiple servers. Parallel iterators are a great way to approach. Because you can use them like you would iterators, but you've got all the async IO in there, you've got the futures in there, you've got the processing across the cluster, and the cluster is really the rationale here. The idea is that if I want to spread my work out around the cluster, I need to be able to describe where the inputs are, and then I need to be able to partition those and serialize those chunks, those partitions, serialize them out to the different workers across the cluster. So parallel iterators give us a way of being able to describe what we're going to process, but then serialize the parts that we send out across the cluster. And so it can operate over effectively infinite sequence of items. It has some transformations built in that are based on method chaining, really, really convenient. And at the end of the day, it's a way of doing sharding. It's a way of doing partitioning. And that can come in very handy when you're working with some set of actors that you're creating, and every actor has its own shard. Would be one of the ways to look at this. There's a more extended tutorial that, again, Dean Wampler did. It's 05 Ray Parallel Iterators. If you look at Anyscale Academy, but I'll be covering some code examples of this. And there's a few flavors, there's a few trade-offs depending on some of the semantic guarantees that you want to have in the results. So we'll talk about that. But the sharding and the lazy evaluation here are super important concepts. Just as a really super high-level example, you run Ray, and okay, there we've got a remote function, and it's going to take in some shard. And then down below, we've got this iterator that we've defined from a parallel iterator. So we call ray util.iter, and then we and one example of this is by giving it a range and then a number of shards. We're also telling it whether or not it will sample with replacement. We're telling it how much to batch, and then we do some sort of apply. And then down below, you can see where we're calling remote on the shard. And that will give us back basically this list comprehension of all the different object refs. And from there, we can just apply get, sorry, we call ray.get with that big list of object refs. And that will come back. We'll show this in a working example. This is just a high level overview, kind of give you the flavor of how you would use parallel iterators. Okay, let me jump back into a little bit of theory. And with a caveat, this is theory. This is very different than the kind of hands-on coding that we'll be doing in a bit here with the notebooks. And I want to also give the caveat that this may seem a little bit disjoint from the design patterns that we just talked about that we'll be using. But once you jump into it and once you start digging into nuances and edge cases and what's really going on under the hood and what kind of trade-offs do you need to make, hopefully this material can give some good background for some of those kind of judgments and also understanding where it applies in the broader scale of large frameworks for distributed processing. So I want to provide this background. And I think that once you dig into this area, you'll also find that some of this comes in pretty handy. So first off, rolling the clock back to 2009, it's very important. There was a paper called Above the Clouds that was done by Berkeley in what became AmpCamp. And David Patterson led grad students on that, also Jan Stojka. They were trying to make a formal definition for cloud computing because at that point, AWS, which was launched in the middle of 2006, cloud computing was only less than 3 years old. It was 2.5 years old when the paper was being done. And they did it. They did a really interesting paper, 17,000 citations currently. You know, for several years, this really set the tone for people to understand what cloud meant and its implications on distributed processing and developing frameworks. It was relatively prescient. It really spelled out a roadmap that AWS and others would follow over the next 5 years or so. And for what it's worth, I got to critique this paper and meet some of this early team back there in February, March 2009. 10 years later to the day, David Patterson led a new crop of grad students to take a look at how cloud had evolved 1 decade later and apply some similar kinds of methodology. A lot of that was led by Eric Jonas, a postdoc at Berkeley, who had sort of grown up geeking out on cloud, you know, building his own AWS simulator when he was in high school. Eric's great. He took this view of really looking at the physics of what's driving cloud or preventing certain things from happening or causing other things to happen in terms of, you know, lots of devices at scale and how do we use them in a cloud offering. But also, how does that impinge on the economics of it? Like, what is or is not going to happen in near term? So they have a paper in 2019 called A Berkeley View of Serverless Computing. And the title may be a little bit misleading, but it's there for a reason. It makes sense if you read through this. Highly recommended. Take a look at both papers. Here's a blog post also on the RiseLab blog from Jan, who wrote sort of a compare and contrast about the two papers a decade apart. The 2019 one really spells out what's going on now in cloud. And so, you know, rolling this back, like I say, to 2009, they were able to develop, they were using a certain research methodology. They talked to a lot of people in industry. I was one of them. They applied a kind of pattern language, which we're using here, to describe what was going on with distributed systems. You know, and they came to the realization really that Amazon had very sophisticated services before they launched AWS internally. The original offering for AWS, to some extent, I think it's fair to say, it was kind of dumbed down because they wanted to make it very recognizable for IT staff who at the time were accustomed to things like VMware. And so you had a lot of emphasis on sort of VMware-ish kinds of ways to leverage AWS initially. There were other things though. There was S3 was kind of a different beast. There were some other things originally launched that were also very, very kind of weird and different, but in retrospect, they made a lot of sense. So, you know, AmpLab really leveraged a lot of this. Mesos project came out of that work, that 2009 paper, and AmpLab that developed out of that. And one of the early projects out of Mesos was something called Apache Spark. I'm grateful to have been able to work with both those teams. Looking a decade later, what they noticed was, for instance, in the lab that created Spark, you know, only like about half the grad students really were running Spark. A lot of people were just using stuff off their laptops. And to kind of put this into context, back in 2008, I was leading a team that ended up fixing some of the, there was a Jira ticket on Hadoop at the time, which prevented it from running efficiently on EC2. And so our team fixed that. Anyway, without going into further detail, we became like one of the largest instances of Hadoop running in the cloud, and a case study for EMR. Not so long ago, I took that data rate and that algorithmic work, which used to run on a large cluster of extra large AWS instances. I took that same data rate and algorithmic work, and I ran it on my MacBook Pro in Python, and it ran faster. What has changed over a decade in hardware is something we really need to take note here, because that's what we're doing with Ray, is a lot of these trade-offs for distributed processing. So there's been a huge evolution in terms of multi-core, you know, starting with the Intel multi-core processors that were introduced in 2005. And that changed a lot fundamentally of where cloud had started. There's been, of course, a lot of change in terms of disk technology. It's not spinning disks, which Hadoop was built on. Instead, you know, we're using SSDs. Memory spaces are much larger. Networking, the IO fabric, all that, much, much different. So things have changed. And this has a lot of impact on what's going on. Eric Jonas and company in this 2019 paper really spell it out. A lot of where we're heading toward is this kind of decoupling of computation and storage, where it used to be not a bright idea to move the compute to the data, rather you move the data to the compute. That was early. Now we're talking about decoupling of computation and storage, and they scale differently, they're priced differently. And the abstraction that we're talking about now is you really want to run a piece of code, you want to pay for the execution of running a piece of code against a piece of data, as opposed to paying to allocate resources that give you the opportunity to execute the code. And that's a subtlety. It's this kind of this third point, but it really has a lot more to do with how the higher level service offerings that are coming out of AWS and Azure and Google Cloud and Alibaba and others, they're really changing and becoming more sophisticated, and they're really leveraging, like I said, this last bullet point. And that is more of a general sense of serverless, not specifically about AWS Lambda, but in a general sense of what we would say in terms of applicative systems and ad hoc analytics, and a lot of what can be done. And this is a lot of what we're doing inside of Ray. It's certainly the case when we're talking about things like remote functions, and realistically what we're doing in multiprocessing and parallel iterators and all this. And so kind of the big picture of what's going on is that if you look at the history of like cloud and Spark and big data frameworks, around 2005, there was commodity hardware for big data. It was mostly about task parallel. It was largely at the time, most of the workloads, I can tell you, they were log file analysis. It wasn't all that sophisticated yet. And it didn't really pick up, ramp into more sophisticated use cases broadly, outside of, you know, Google and Amazon maybe, and a few others. But more broadly, it didn't pick up in industry and enterprise until like the early 2010s. Around 2009, you know, there was more of a recognition of data science as a thing. And the kind of workloads that were more interesting then were moving out of what had previously been going on with enterprise data warehouses and analytics based off of data warehouses. Instead, having data science workflows and machine learning. A lot of what was going on in 2009 really leveraged actor pattern. Certainly you saw that with Akka, you saw that going into Spark, etc. But then yet another 4 years later, this whole arc from 2005, 2009, 2013. After 2013, of course, you had deep learning pick up. There was the AlexNet paper that was published in 2012. Realistically, NVIDIA got into the game with deep learning back with the workshops at NeurIPS in 2009, but it really picked up around 2013. And it's a very different kind of processing because it had a lot more to do with manifolds and gradients, differentiating gradients, the kinds of things that you do under the hood for machine learning. And it's a lot of network data. And so I want to draw this as an important point when you're looking at applications. The world of 2005 and Hadoop had a lot to do with log files. And then you get into actor pattern, and then you get into something that's much more of like point-to-point networks, talking very, very fastly. There's a great discussion of this by Jeff Dean. This was a talk that he gave at Bay Area ACM meetup back in 2013. And it was long before anybody in public was talking about a thing called TensorFlow. But Jeff Dean is describing the new generation of Google data centers and the kind of IO fabric that's gone into those that's different, and processing workloads of a lot of very large scale neural networks that's very, very different. It's not the world of Hadoop and Spark and MapReduce. It's about point-to-point communication between nodes in a network. And how were they optimizing that? What kinds of distributed design patterns did they have to leverage? So just to summarize this, back in the 1990s, if you are working with parallel processing, for instance, in life sciences, you're probably still working with this stuff, but we were using MPI and message passing. Oddly enough, that has some similarity with what we're doing with actors. But then we got into the aughts, and following up from work that had really launched back in '97 from eBay and Yahoo and early Google and others, we had things like Hadoop and Spark. And instead of having this kind of haphazard message passing spaghetti of MPI, instead we had phases, and we could do different kinds of processing across a cluster that were synchronized in phases: map, shuffle, reduce, things like that, managing the width of aggregations in Spark. But the downside of that is that if you have very asymmetric data, you can go, have some straggler nodes working with really large data entities, whereas the rest of the cluster, its utilization drops to almost zero. And so as we get into more and more sophisticated kinds of machine learning, that becomes a problem. Going back to the Jeff Dean talk, he sort of illustrates it. It's more a matter of, can we take a network that's complex and have the different nodes talk with each other and be able to do things like neural networks, deep learning. And this is where PyTorch and TensorFlow and Ray optimizing them really come into the picture. And so that's kind of generationally what's been going on and why this has impact on your applications, depending on the type of things that you're doing inside of your applications. Okay, I better get busy. So let's cut over now. We're going to be working with this repo, and we've put it into the chat a couple times. I hope, and also sent out earlier message about it. If you haven't already, go to GitHub. Rather, you can just use this line here, but clone that public repo, Ray tutorial, and then connect into it. And the README has instructions on how to use pip or conda to install the dependencies. And let us know if you have any problems with the dependencies too. We've been working through a lot of different issues, certainly depending on the kind of environment that you have, but hopefully between conda and pip, we've got a lot of that worked out. I see a couple chats. Okay, nothing I need to worry about. All right, I'm going to leave out of the slides here and cut back over to, where are we at? Okay. So if you go through, here, let me show. Here is the repo on GitHub, and this is Ray_tutorial. If you go through that, it's got instructions for cloning, and then once you get in, maybe you want to work with a virtual environment. That's up to you. But if you're using PyPy, if you're using pip to do installations, requirements.txt should handle it. And if you alternatively, if you're using Conda, then you can set up a Conda environment. We show some instructions there, and then just use pip over the top of that. That's going to be the best way. I've been working on an environment.yaml for this, and Ray and Conda are not exactly friendly to each other, although they're fine if you install Ray through pip on top of Conda. Once you've got that, then you can run Jupyter Lab to access all of this. And there's a great question that came in from Mode. Does Ray support 3.9, Python 3.9? Yes, it should. One of the other systems I was running on was running Python 3.9. I haven't run into any specific issues. I can take a look after the course to see if anything's been reported, but should be okay. If you have any troubles with that, let us know. All right, so here's a description of the course. Basically, we're going to run through all of these different notebooks here, linked in order. So once you launch Jupyter Lab, then that should pop up in your browser. It should be, if you're not running an earlier instance or something else that uses the port, it should show up as localhost 8888. And so there. Now I'm going to shift over and work with some of these notebooks here in Jupyter Lab. The first one, the simplest case, is with remote functions. So here, I'm just going to step through these, but I'll be describing. Try them out. You've got the notebooks. These hopefully are a good starting point if you want to use these kind of patterns in your applications. There's also some points here where you may want to go in and change the parameters and rerun them and see, kind of play what if. I'll try to note those. But first off, this is going to show how to use remote functions for task parallelism. And so the very first thing we'll do is to say import Ray. We've got a couple other libraries. I'll import logging just so I can basically turn it off so it doesn't clutter. But I'm also using a library that I really like. It's called Ice Cream if you're working in Python. And particularly if you're building libraries, Ice Cream has some really nice properties for being able to trace things independent of any IDE. So I may be using that later on. I just sort of stick it in there to be sure. We're going to start Ray by saying ray.init. And we're also going to give it a flag, ignore reinit error. So if you already have Ray running, then it'll just pick that up as opposed to trying to collide with it. And then I'll turn the log level down to error. So hopefully we'll see a lot less logs because it can be really verbose. And then lastly, we'll show when Ray is running, we'll get a URL here in a moment. When I run this, it'll be the Ray dashboard. And we can use the Ray dashboard to be able to explore a lot of what's going on. Let me take that up. Okay, great. So when you run Ray init, it will come back with, well, one of the variables gets populated. It's a function call. You can figure out where the dashboard is running. In this case, localhost 8265. And if you bring that up in a browser, now you can take and start to explore what's going on. This right now is running on my MacBook Pro, and I've got 4 cores on the CPU. So you can see that Ray has set up 4 different workers there on those different cores. All of them are idle. There's nothing being run on Ray right now. But we've got a view into what's going on with the CPU utilization, how much RAM there is, how much is being used, I/O, and there's some different views when we get into this. But at the end of the day, when you're trying to analyze where to parallelize an application with Ray, being able to understand where the usage of CPU, memory, disk, I/O, all of these are considerations for where to make those trade-offs. Because realistically, all the patterns that we're exploring Each one of them provides a lot of features for parallelization, but they also incur some overhead. So you want to make sure you're using the right ones for the right cases, that you understand what kind of overhead is involved. And you do the profiling also using Ray Dashboard and some other methods will show. You do the profiling so that you can really get the information you need to make those trade-offs intelligent. Okay, so for this example, it's real simple. We're going to import time and random just to be able to use them. And then we define a function, my function. It returns the value, which is the answer to the question meaning of life, 42. If you call it function, you get back the answer to the meaning of life, which is 42. Now, if we want to make this a remote function, if we want to parallelize it, we just add the decorator to the top there. Now, when we invoke it, we'll call myfunction.remote instead. And if there were any arguments that were required, we would just add those as arguments for remote, and it'll pick up its args and quarks. But what we get returned back is an object reference, a future. So run that, and you can see the object ref. And now we can use that object ref to go out and retrieve the value, compute this function, retrieve its value from across the cluster. Boom. And there we have the answer to meaning of life. Now, the invocations of remote functions, these happen in parallel, and all the computation is performed out there in the background. It's driven by Ray's event loop internally. Let's illustrate the idea of a relatively slow function. So I'm going to put a sleep into this one, and then it's going to just return some random integer. And we'll call this multiple times. Okay, great. And so that's slow function, and basically what it's doing is it's appending a future. Okay, great. So we've got these 4 object refs. And then at some point in time, we can go out and just call them, boom, boom, boom. So the idea of like collecting the object references, that can happen in your application. All the processing is farmed out across the cluster, and then you've got this collection of object references. At some point in the future, you can just go and call get on all of those to get back the values. So that way the processing happens distributed remote. Now there's a few nuances of this. You may want to wait. You may want to do this in an asynchronous fashion, or you may want to do this in a synchronous fashion and just wait and sort of get these results as fast as you possibly can. There's a few flavors of that. I don't have that. We'll look into that in a couple of other ways later on, some of the other pattern stuff. Lastly, I'll call Ray shutdown just to be nice and conserve some resources. Okay. Next up, let's call remote methods. And so here, same thing. We'll set up Ray, and it should come back with the very same dashboard. It does. So it's basically used this parameter here to connect. Well, actually, we shut down the previous Ray, so it's just starting a new one. But we've got the same dashboard running here. I'll refresh it just to stay honest. Okay, now we've got the counter class, and again, all it does is it has state representing some internal value, an integer, and we've got a method that will increment that. We'll make an actor out of it by using the Ray remote decorator, and then we can instantiate the class as an actor by calling class remote. And again, if you had any parameters to initialize, you use them there. And now we call counter with the increment method dot remote. Again, add any parameters you need to, and then call rayget from that object ref, and you get back the value. So using actors is very, very simple, very straightforward. And I'll just shut that down just to keep things tidy. All right, now let's take a look at objects. Okay, so start up Ray, and it should have the same dashboard. Okay. And now what we're going to do is just have a value. Here's an object that we've created, an integer y equals 42. And we'll say Ray put on that object. We'll get back an object reference. and then call array get on that object reference and get back the answer, again, the answer to the meaning of life. And you can use these across a list comprehension if you want to do this in parallel. I'm going to show what happens if you've got one that's long running by introducing time sleep. And then we'll call this with a timeout. So if we're trying to access an object and it just takes too long to get it, we can have some try-catch logic, basically. Okay, great. And it threw the exception. Ah, the name error. Sorry, time was not imported. Let's run that again. I forgot to run one of my cells. Boom. And this should time out after 4 seconds, right? Okay, great. So we've done some try-catch logic there, and we did our exception handling. Okay, so the main thing about objects is that it's got the same calling sequence, array.get, on the object ref. It's the same calling sequence that you use for remote functions and for actor pattern in remote classes. So that's a consistent way of accessing 3 different patterns. And finally, just call array shutdown, just to play nice. That's great. Okay, now let's do, whoa. And something didn't like sure. Let me restart my kernel. That was something on, it's not the code. I'm going to blame that on Xcode and things going on my MacBook Pro. Okay, so run this. It should have the same dashboard. Boom. And just to keep it honest, great. Now with multipool, really straightforward. It's a drop-in replacement. So we call array util multiprocessing. We import the pool object from that library. And then here, we've just got a simple function that will apply to iterators out of with a pool. So we instantiate the pool, and then we call it in this loop. Boom, boom, boom. Great. So again, what we're doing is this is an applicative system and illustrated very, very explicitly here. We've got range. This is the input. This is an iterator. And we take this whole pool and apply this function across it. And then we get back the results that we can iterate through. Again, this is something, it's a pattern that's used in Python programming a lot. So here's a drop-in replacement to be able to distribute that processing across the cluster. And then just to be nice, we will shut that down. Okay, good question from Mode. How does remote objects, how does that help run tasks in parallel? Well, okay, think of this. Perhaps there are values that you need to have accessible by the remote tasks. And rather than serializing those out across the cluster n times, like if you have 1 million tasks, do you want to take some configuration or some data objects, whatever, do you want to serialize them out for each and every task? Probably not. That's a lot of overhead. So again, we have to look at the overhead costs of applying a particular design pattern. With task parallel, as long as we have data independence and we have a statelessness in terms of the units of work, the chunks, we're good to go on task parallelism. But what that means is we've got to get all the input data and configuration out to all those tasks running in parallel, and they're somewhere across the cluster. So we have to be able to serialize things, and that incurs some overhead. So by using remote objects, we can just sort of drop things into the object store, and then everybody can access them from some known place. They may be singletons. There may be reasons why you want a particular thing with a specific value. So it's some shared memory. It may be something that's large, and therefore replicating it across the cluster would actually deter your capabilities for processing. It may be that there's some type of caching, some intermediate states that the actors are putting into an object store, like you chunk through a few stages of your application, and then you come out with some intermediate results that are cached that can be reused later on. This is something that's seen a lot in data science workflows, like for instance, when you're doing a lot of data preparation and then you go to another stage where you do some feature engineering, and then you go back, and after that, next stage, you're training some learners, and then after that, next stage, you're doing evaluation of different models. So sort of, doing your grid across different hyperparameters. At some point, you need to refer back what were those features and test against them or compare them. So you can think of, like, at every stage, there may be some products coming out that are, intermediate cache results. That's a very typical thing you see in pipelines workflows. And so that's hopefully that answers some of why you'd want to have an object store and why you would want its access patterns to look a lot like the computation. Because when you're breaking down the DAG of like a complex workflow, parts of the elements of that workflow are things that you'll want to store in cache. Parts of them are just so cheap, if you lose them, you recompute them. Again, you want to understand where that trade-off is. So the stuff that you want to cache, you stick in the object store because it's too expensive to recompute it. The stuff that it's probably cheaper and faster just to recompute it than it is to store it, you make that a remote task. Hopefully that answers that question there. Really great question, by the way. All right, let me get to joblib. This one's a little bit more involved. Again, we'll launch Ray. We'll get the dashboard going. Now here, what we're going to do is, the main thing here is from Ray util joblib, you import a function called register Ray. The rest of this has to do with what we're doing in scikit-learn. Now again, joblib is the back end for processing in scikit-learn, and what we're providing here is just a drop-in replacement. So we call register Ray to tell scikit-learn we're going to use that. And now let's go into scikit-learn land. We're going to load up the UC Irvine data repository. Sorry, let me scroll up. We're going to load the digits, handwritten digits data set that's very popular in machine learning. And now what we're going to do is define a parameter space for scikit-learn to be able to understand how to optimize hyperparameters across a grid for, we're going to train a support vector machine and SVM model. So down here, we've got the support vector. It's using an RBF kernel, just parameterizing that for scikit-learn, but then we're going to apply these different hyperparameters. This is something that AutoML is kind of the approach to doing this in a more smart way, but you can do this more explicitly with pipelines in scikit-learn. So we'll run that. That sets up our parameter space. And now we can call randomized search across a grid there to do cross-validation. We'll use 5 cross-validation splits, 10 iterations each. This results in 50 different fits that we're sampling, that we're measuring. And this should be enough to at least illustrate what joblib is doing. So we're going to search across this space and find out how do the hyperparameters fit for the given data and kind of algorithm support vector machine. And so that's going to do some running, right? So far, we've just set up the pipeline. But now what we're going to do is say with joblib.parallel backend Ray. So we're identifying what we register Ray. We're going to say do this cross-validation to fit the data, train these models, and see what the results come back with. Okay, and now you can see it's starting to do its fit. Let's click over to the Ray dashboard. And now over here, you can see pool actor. You can see some things running. I've got each CPU vaguely at 31%. Now there's a little bit of imbalance there. So there's a couple that are running batch. Yeah, cool. Okay, great. Should be done. That was pretty quick. I didn't want this to run too long, so I kind of dumbed down the example. So it's really only got 50 fits it's doing, but it's enough to be able to illustrate the case. If you wanted to, you could go back in and change this so it isn't just 10 iterations, make it 1,000. And then you can really see the interactions of what's going on inside of Ray dashboard. Of course, it'll take longer to run. What did this produce? Great. Here is our best fit. Coming back from scikit-learn, we've got our gamma and our c-value, etc. And so now we could go back in and train this model with our best hyperparameters. So there you go. That's a form of AutoML. Hyperparameter optimization, so to speak. But really, this is just showing a drop-in replacement there for the scikit-learn backend. And that comes in really handy. You know, you use those patterns correctly. It's very useful. And so this is a good point to get back to the question that Louis had earlier. Can Ray be used to parallelize network X? And this has a lot of bearing also on scikit-learn and other popular libraries, pandas. So I want to step back a little bit and talk here. What we just have shown was a kind of pipeline in scikit-learn. And let me step back and say that when you're working with big data, when you're working with these large data workflows to be able to train some machine learning models or whatever, typically the front of the workflow, the front of the pipelines, you're doing a lot of data ingest, ETL, a lot of data cleanup. You're working with fairly higher data rates to do big joins. And then from there, you start doing some queries and other processing to kind of pare it down until you've got your features. So the early stages, you've got a lot of data, and frankly, there's going to be asymmetries in the data. There's going to be a lot of sparseness. Typical kinds of pre-processing might be doing some dimensional reduction, like you would do in clustering or singular value decomposition, various forms of non-negative matrix factorization. That's kind of sparse, and that's something that's distributed across workers across a cluster, typically. Once you get into the later stages of a workflow, then what you're doing is basically distilling down the data into the features that you use. And while at the early stages, it may be very large sparse graphs or very large sparse matrices, in the middle stages, when you've got your training set, or you're ready to run a graph algorithm or something like that, the data becomes much more dense. And so there's this kind of shift in priority from, like, I call it thinking sparse and dense. And there's actually a book that I'm helping write with my colleague Dean Wampler on behalf of NVIDIA. I guess I shouldn't announce it too much, but we'll be coming out with a report, a little mini book soon. This is one of the areas we're exploring, is how to think about these workflows and how to really get the best out of your hardware. So at the early stages, you typically have more data asymmetries. You're working with big data tools, do your data preparation, et cetera. When you get into the middle stages of a pipeline, the data becomes more dense, and then you can start to apply the hardware, because this is where things like scikit-learn and PyTorch and other means of leveraging hardware under the hood through Ray, for instance, or through Dask, but with Dask on Ray. This is where you can really take advantage of the hardware. But having said that, to go back to the question about network X assumes that a sparse graph has been placed into a very dense matrix representation. Almost all the algorithms inside of network X and inside of iGraph and other similar kinds of libraries, they assume a dense representation as a matrix. And therefore, this is where you can use libraries like CUGraph out of Rapids, where they will be accelerating what's going on under the hood because of the denseness. The earlier stages of how do you get to that matrix representation of your graph, that's where you can really leverage Ray. So short answer is, much of what's going on in network X, you probably don't want to worry about parallelizing it with Ray. There is work to parallelize it under the hood by sort of how does network X build on top of pandas representation, because then you can leverage libraries like CUDF and CUGraph. But there's also the notion of sometimes you just want to use a block of data and take a graph algorithm and parallelize it that way. And so that's sort of block processing for graphs. We can get into more detail there. There are applications there where things like Ray can come in handy. And I've got some plans to do some graph processing if anybody wants to join. So that's where things like RDFlib could be parallelized with Ray, whereas it would be more difficult to parallelize those with something like CUDF. So let's see, another question came in, is there a pool map async function that works in Ray? I will have to look up how that would be translated or could be translated. Nothing off the top of my head for that directly, but I may be very, very wrong on that. So I'm just sort of answering off the top of my head. Or pool start map, or sorry, pool star map.async. Huh, that's cool. I haven't used star map.async. I will have to look and see from the multiprocessing library proper what the other methods are there. Okay, great. Other question, can the data object in the object store of a specific node or cluster be accessed by another node without replicating? Right, so, okay, so there's a question there about the object store and remote objects. You don't know exactly what node an object lives on when it's in the object store. So yes, it can be accessed. It would be accessed over the network. So you don't have guarantees about where an object lives. But if you needed strong guarantees about, for instance, having some large piece of data that persists and having it being tied to specific processing that's applied to it, in that case, you'd want to leverage an actor pattern explicitly and have that piece of data be part of its state. Typically speaking, that's my takeaway on that is the object store is more of a caching layer, but what you're talking about with this question here is more of the statefulness of a particular stage. I could go into that in more detail afterwards, but long story short, if you really want to prevent any sort of replication across the network, then you probably want to be leveraging actor pattern for that instead. And it's not hard, fairly similar ways. Great question. Ray, okay, another question from Mo. Does RayTune work seamlessly with scikit-learn, like in this joblib example? Great question. So RayTune can be over the top of the pipelines using in scikit-learn. It would be also using Ray, but at a different layer. And so you could be doing like hyperparameter optimization or model selection, things like that in a scikit-learn pipeline. But then you could also have joblib as like the backend for the scikit-learn to use for the algorithms that are implemented. So does RayTune work seamlessly with this? Yes, in the sense that the same Ray cluster can be doing this in parallel, and Ray will be doing some optimization across the resources. But what I showed with joblib wouldn't necessarily have any tight coupling with the optimizations that are going to be happening out of tune. I hope that answers the question there. We can go into that in more detail. And Peter Rose has a question. Can you compare contrast Ray with Spark? Okay, real quickly. Ray is providing a lot of design patterns for parallelism, and these are similar kinds of things that are used in Spark. Ray has the reinforcement learning. Well, Ray has some optimizations for TensorFlow and PyTorch that can be used for machine learning in general. And then Ray has RLlib, which is another layer on top for reinforcement learning, and also some of the environments that are being simulated with reinforcement learning. And it also has RayServe and some other elements for being able to serve models, really fast across a microservice grid. But then there's also things like RayTune. So there's a lot of different elements in Ray, and it's building up a very sophisticated tool set, if you will, for being able to run sophisticated multi-cloud clusters. Spark, on the other hand, is really looking at data workflows and sort of deconstructing a complex SQL query into something that can be a data workflow and then running that parallel on a cluster. So it's kind of an apples to oranges comparison. They're not exactly the same thing. There are reasons why you want to use Ray and Spark together. Even if you use Ray to the max, there's still reasons why you need to use Spark. So, I won't say that it's a replacement. It's definitely a different philosophy when you look at what's under the hood about what's going on and what's exposed to the user. For what it's worth, I used to be the evangelist for Spark, and now I'm in a position here working with Ray. So, there's an interesting compare and contrast. We can go to that in more detail, but I hope that starts to answer some of the question. Okay, one last thing, and then I'll jump into the part that I've really been wanting to feature. So just real quick, we'll go through parallel iterators. And there's a few different flavors of this going on. So you may want to dig into not just this, but also what's in the manual. There's some good references. So first off, we'll show, here's a collection, the integers 1 through 5. And I'll create a parallel iterator from it by just, wrapping over that collection, that list. And then I'll tell it how many shards. So I want to have 2 workers assigned to it, 2 partitions. This is sharding it into 2 shards. And then I get back this handle, this iterator. Now, this iterator is something that can be serialized and sent across the cluster. Or you can run it locally. If you want to evaluate what's going on, you can call, you can convert it into what's called a local iterator. And then I can gather the items, and I'll show one flavor of that, doing that synchronously by gather sync. So we'll say iter1, our iterator, gather sync. That'll give us our local iterator. And then I can just run that in a loop or a list comprehension or whatever. Run these, boom, boom. And it'll iterate through our sequence. Now, understand that what we've done there is we have a semantic guarantee that when we run gather sync, the synchronous part of this, we will get back the results in order. So we're preserving the fetch order. So if your application absolutely needs that order preserved, then you want to provide that guarantee. You want to do this in a synchronous fashion. But if you relax that, first off, let me just show an example of it. So I've got a cumulative sum, and when we apply this, so we'll do gather sync. So we've got our iterator. We're taking and applying this class using the call method here, what it does, and it'll just do a cumulative sum. You can see it does this, right? Alternatively, we can use an asynchronous approach. Okay, and so now I can grab these different shards and just run them in parallel. And what you see is the order is not preserved. So I get increased parallelism by relaxing that semantic guarantee. So if the order is not absolutely important for you, you may want to use async instead. You can get some more performance out of that. And there's a few different flavors of this. What I'm going to do now is actually implement, there's a kind of word count that we were running. Basically, we're taking all of the text out of the notebooks in this repo, and we're looking at the markdown in the markdown cells, and then we've got a sliding window across them, and we're going to come out with the occurrence of words. So we farmed that out in some, using this sliding window across it, we farmed this out as a parallel iterator. We've got 3 shards defined, and boom. We come back with what's the frequency, Kenneth. Okay, and now just for grins, we can come back with a word count out of that. Boom. And so if you want to look at something that's kind of MapReduce-ish, here's a distributed word count done using parallel iterators and in Ray. Okay, we have 4 minutes left for the time allocated, and I want to get to the part that I really want to talk about. So let me shut this down. We can go into more detail afterwards if you have questions. I'm willing to stick around. And obviously, we can go online. I can show some forums where we'll be at. But what I want to do next is pull up Py notebook, Python notebook. We'll launch that. What we've done here is to show a number of different methods for profiling in Python. And let me just check and see if there's any questions. Good. Chat is, oh, good. Okay, thank you, Sophia. Yeah, Sophia sent out the form for some feedback. We'd love to get your responses about use cases that you're interested in, feedback about the material here. Certainly use the GitHub issues if you have anything that you want to update on this repo or in this tutorial. Okay, what I'm going to show real quickly here is a few different approaches for profiling in Python. And so this is something that augments what we've got with Ray Dashboard. By the way, this should all be winding down. So what I'm going to do is basically approximate pi in a parallel fashion. This is building on something that Dean Wampler wrote out of one of the earlier tutorials. We're using a Monte Carlo method to approximate pi. And we'll show how to use remote functions and then measure the difference between running it serially or running it in parallel with remote functions. And hopefully also we'll get a pretty good trace there on some of the overhead cost of what does it mean to apply these kind of patterns in practice. Okay, first off, I'm just going to use watermark as a way of just getting a trace on what's going on. You can see that here I'm running Python 3.7 and I'm on Mac OS X. I've got 4 CPU cores. Okay, so launch Ray. Boom. Great. So this is our dashboard. Let's just make sure. Great. Now, the application code is pretty straightforward. It's Monte Carlo method for approximating pi. So we've got this function called estimate pi. We give it some number of samples where we want to repeat the estimation. And we're just going to use a NumPy array across that range of samples. So we'll be computing this in parallel because of NumPy to some extent. Although without running Ray, it's not parallel yet. So, just kind of the usual suspects of NumPy, pandas, statistics, and then matplotlib that we use to visualize it. Boom. Okay, now we're going to also create distrib estimate pi by using ray remote decorator to create a remote function. And then we've got this this function here, which will run an epoch. So I will say, in each trial, I want to run some number of samples, which may be very large. And then I've got some number of trials to repeat, and I'll aggregate the statistics across each trial. And I've got a flag for, do I want to run it in distributed mode using remote functions with Ray, which is this line right here, or do I want to just run it in serial mode, use just simple list comprehension. And I will track the duration across that segment, because that's interesting. We're going to parallelize that and then compare it. But then also, just as part of estimating pi, we'll take a look and see, okay, what value do we actually get? What's the standard deviation across a trial? Across an epoch? And then also, what's the error rate across an epoch? So for when we're running each epoch, we'll return that. How many samples do we run? What was the duration? What values do we get for approximating pi? What was the standard deviation of our samples? And also, what's the error rate of our samples? Okay. And now what I'm going to do is just wrap this in a class that will simulate things for me. So I can give it some parameters in the constructor, and then I can just call this function run. And what it will do is run everything according to the parameters and return back a data frame to describe it in pandas. And then later on, I can come back in and call plot to basically, chart out diagrams about the data frame results. Okay, great. Having defined that, let's start to run some things. So we're going to use a few different kinds of profiling tools. Object Graph, Trace Malloc, and PyInstrument are the main things, but also be using cProfile under the hood. And I've linked each one of these if you want to dig into them. But first off, we're going to take a look at memory usage. First off, let's bring in these libraries. Great. So we're going to look at memory usage first. And one of the tools is to use something called Object Graph, and this will track object creation. So taking a high-level view of how memory is being allocated, you can use that to understand the referencing across from one object referencing another and actually plot it. But you can also do a contrast, do a delta to find out where the object growth happens during different stages of processing. So that's one way of being able to track memory leaks or overhead that's being incurred because of how you've done your classes or how you're architecting your application. So first and foremost, before we run anything else, we're just going to get a snapshot here and show the counts for the various the top most frequently created objects. So you can see functions, dictionary, tuple, list. These things are being created more than anything else. Now, we're going to come in and run the simulation not distributed. So we're running it serially. And we're going to give it num samples. I will dig up what num samples was. Looks like 1 million. Okay, so we're going to run 1 million samples with 20 trials each. So we're going to create this class, and we can just call that class .run when we want to run our pi estimation. Now, I've added a decorator, %% time, and so that will be basically give us some wall clock estimates. But if I run it here, you can see the previous results, but I'll run it real quick. And it'll come out with, a real simple view of how much time do we run for. Again, we're running this serially. And the objective here is that I'm going to run it, and then I'm going to take a look and see what's the delta. How did this change in terms of how many different objects were created? Okay, so this tells us the wall clock time was 17 seconds and change, total CPU time in terms of user and system space. But when I run this, okay, so it comes back and says, well, we're creating some dictionaries, definitely, because we know that as we run our simulation, that's what we do. There's weak references, yep, no joke. We're lists being created, but you look at the numbers, not a lot. So when we run this in a serial fashion, hopefully we don't have any memory leaks. I mean, that's one thing. We should already have a pretty well-defined simulation. But if we did, they should start to pop out, especially if you run the simulation for extended periods. So I just want to provide this. I don't think it's going to show anything, useful information for our case. But if you are working on building an application and parallelizing it, you want to check for memory leaks. And so here I'll run a thing. What it does is it will generate a graph of, and depending on what you're doing, this may become a much more complicated graph. Yeah, there we go. And so it's got an interesting graph in terms of all the references of one class to another, who is creating what types of objects. So if you have any problems in terms of your architecture of class hierarchy and who's calling what and who's creating what, and therefore introducing some memory leaks, this is a good tool, Object Graph. It's using GraphViz under the hood. Now, at a lower level, you can use tracemalloc, and this will show you what kind of memory blocks are being allocated by Python. So this is more at the system level, less the application layer. But what you do is you say tracemalloc, which is built into Python. You say tracemalloc start, and then I'm going to run our simulation again the same way. And then as soon as it completes, I'll take a snapshot. And that's good because now over successive runs with different parameters, you can collect a lot of different snapshots and then start to compare the contrast between them. So if you do have memory leaks, now you can start to get this trace back at a low level of exactly where they're coming from, or hopefully, maybe exactly is the wrong word, but close to where they're coming from. You can also get statistics about how the memory blocks are being allocated per file or per code line, get some stats back, and then be able to compare and contrast between snapshots. Here, it's going to show us some things, not a whole lot, but you can definitely see what's going on in terms of some of the overhead. Realistically, we've got some pandas that's being created. Obviously, we're collecting our simulation into the results going into pandas. Again, we don't have a lot of problems with memory leaks, hopefully, in this example. If you did, these would be like a 1-2 punch for being able to examine that. And that can be really useful when you're working with array to parallelize. Now, the next step up is something very typical in Python, deterministic profiling. This is more about CPU usage. So a deterministic profiler is going to measure our call stack. And for this, we're using something called cprofile. And you can call that explicitly using a magic called prun. It's built into Jupyter. So %%prun, I'm going to run it in quiet mode and look at results later. And I'm going to save the results as text out to a file, prof_cpu.txt. Now, having done that with the same profiler results, I'm also going to visualize them. It's using a library that I really like a lot called SnakeViz. We'll take a look at it, but it'll show us an interactive visualization of the profiling. So we'll run that. Again, the same simulation run again, over again, 1 million samples, and pretty soon you'll see SnakeViz pop up. Let's just run this through. I know I'm a few minutes over, but I hope that this is helpful. Come on. And I did only 1,000,000 trials just because I didn't want this thing to run for minutes. Great. So now this is run, and we've got SnakeViz. There's a few different parameters. Like if you want, you can get a sunburst. If you want to drill into a sunburst, it's pretty cool, especially if you've got a big display. I'm here on a laptop, so not so big. I'm going to kick back to Icicle, and then I'm going to drop down to depth 15. Now we can examine the call stack. So we can see that we're running from the notebook. Then we run our simulation run, and then it's got a list comprehension in there, and then it calls an epoch, and the epoch has another list comprehension that calls estimate pi many times. And as you can see, there's a split down here. If you dig into this, it's basically showing that at the end of the day, let me get this back. At the end of the day, most of what we're doing is being chewed up in CPU time inside of estimate pi. And we kind of knew that coming in, but SnakeViz is a way to really break this down. So again, that's deterministic profiling for CPU usage. And it has a lot more details if you want to dig into them. Now, all of that is also available here. I saved it out to a file if you want to take a look and dig in at the cumulative times. And there's other tools to be able to look through this kind of profile. Now, alternatively, what you can use is a sampling profiler. So cProfile has some overhead. It's examining the call stack, but it really kind of gets in the way a little bit because there's overhead on each call. Instead, you can do a sampling profiler, which is much less getting in the way. So there's one called PyInstrument. I like it a lot, and it will do statistical profiling then of the call stack. And so we'll set that up again, start, and then stop to get a snapshot. We're running the same exact simulation, and this should pop out with a display pretty quickly here. Let this go. Okay, great. And so now PyInstrument is going to show us the call stack, statistical sampling, and it's going to break it down. And this is where we can really start to see where the overhead comes in. So here, we've run our simulation, got a list comprehension, run an epoch, it's got a list comp, and then estimate pi is really the big deal. And realistically, it's a matter of milliseconds of overhead for all of these, just given the kind of parameters we had. But the real processing is almost all down there inside of estimate pi. So that's the thing that we're going to parallelize. And if you want, you can dig into more details. But I really like using PyInstrument. There's another one called Yagi. It's built into PyCharm also. It's a little bit problematic to install in some cases. It's a good tool, a little flaky on some parts, but I'm not going to disparage it. I like using PyInstrument. Okay, now we know that we've got some bottlenecks if you run this serially. Let me plot out the run that we just did. So I'll do a simulation. And you can see here the duration, as if we start out with just like one sample or two samples, it's low, and then it spikes up. And so you can see this kind of starting to trail off here. This is a log plot, so we are getting a nice growth there, right? But then you can also see the error. See, it starts out very high in our simulation, as you expect. But as you begin to get into larger and larger numbers of samples, this is going to drop precipitously. So it drops, but then it bounces around. It's a stochastic process. We expect that. But the real information here is the standard deviation. So we're trying to approximate pi, and that's an irrational number. Even if we don't know what pi is, we can still measure the standard deviation of our samples. And as those drop down closer and closer to zero, we can throw in some kind of cutoff. That could, if we wanted to rework this, we could do an early termination clause by having some threshold on our standard deviation. And this is used a lot in numerical processing. For instance, the power method of PageRank uses something like this, also for a stochastic process, which is PageRank, but by comparing successive iterations of raising the adjacency matrix to different powers. So I just want to show that if you're doing a lot of distributed processing on some large simulation, even if you don't know what the value is supposed to be, which you have to do if you want to calculate error, instead you can just use this simple trick of like thresholding on the standard deviation. Anyway, these curves are kind of what we'd expect. And if you want to dig in, we'll just show, a describe on the data frame to show what these different values look like. Now, let's change this around. We'll just change one parameter, distribute equals true, and we'll take a look at running this with remote functions. It should run a lot faster. And I'm not going to repeat all of the processing that we did before. We'll leave that. But I will look over here. You can see that it's running, it's using up some CPU. And it's running across a different, bam, and then it's done. Okay, now we'll come back through and plot it. Again, this is a log plot on the y-axis. So the curves look roughly the same. They're kind of dampened a bit, but they are different. So there's been a linear speed up because we sent this processing out across 4 different CPUs. And if you look at the raw numbers, you can actually see it better. You can see quite a bit difference in the max duration. Let's go in and take a look at this in a more analytic way. I'll use scikit-learn and I'll run a polynomial regression. Now I'm going to run a polynomial regression with a default. The degree is set to 1. So this is a linear regression. If you wanted to study this as a more complicated polynomial, here's the code to do it. I know for a fact that this is going to be a linear speedup. At least I certainly hope so. So it's kind of a little bit overkill, but it's there in case if you ever want to reuse it. What I'm going to do is take the 2 successive runs, serial and parallel, and that's ys and yd, that's the duration variable, versus x, which is the number of samples. And I've created a pipeline here to be able to do a curve fitting prediction of those lines. And so now we can just do a plot and a line, and you can see there's the serial, the green line, that's fit, and it's a linear ramp, we know. Of course, it's a stochastic process, so the actual measured points are going to be kind of all over the map, but there's a good line fit. The red line is distributed processing. And the really important thing that I want to stress here is right here. When you're doing this startup with really low numbers, notice that the distributed version is more expensive. So there's overhead by having remote functions. Not much, but there is overhead. Now, when you have remote functions and you have remote objects and you have parallel iterators and you have actors and you pile all these things on top of each other, the overhead grows. So you really want to understand your problem and where the bottlenecks are. Are they CPU, are they memory, are they IO, are they disk, whatever? And are they stateful? Is there data independence? All of these factors come into deciding because there is overhead. But in this case, we've got data independence. We can farm things out across 4 CPUs. So you see this red line is distinctly lower. Now let's go ahead and measure the relative slope of those 2 fit lines. And I hope this works out. Boom. Yeah, so we see we get a linear speed up. Asymptotically, we'll come out to a median value of 1.58 speed up. And the fact is, I'm running a laptop. I'm running Zoom. I've got my network going on. I've got all kinds of things going on. So I don't get the benefit of the full 4 cores, but I do get speed up. And hopefully that's showing something. Now, if you want, you can go back in and rerun this with other parameters and watch what's going on over here in the dashboard. It's really interesting. I mean, we're not going to be able to show any sort of memory bottlenecks or IO bottlenecks because this is a compute-bound process. But those would be the kind of tools you'd want to look out for, right? Now, in the time remaining, let me do one more thing. Link to the code repo out. Yeah, okay. Maybe, Sophia, if you can provide the code repo link in chat one more. There was somebody who was asking for it. Now I'm going to, if this works, hopefully this works. Let me go back and share screen, stop my share on this one. I've got another box and I hope this works. We tried it out earlier. Yeah, let's go for it. And let's go back here. Are we on? We're on, good. Okay, so I'm gonna shift over now and run the same thing again, just real quick. I'm gonna rerun the kernel with all cells. And so I'm on a box, it's called a K-Focus, and it's an Ubuntu laptop, but it's got a GPU in it. And let me run this thing. Come on, start. Brilliant. I have no idea what's going on. Ah, good, good, good. Okay, something died. Wow. Okay. Okay. Load. Oh God, sorry, that was out of order. Live demo, you know how this goes. Come on. Wow. Okay, something got fried. You know what? I'm gonna cut over to questions. I thought I would get that worked out for this demo, but we're over time anyway. So let me cut back over. Yeah, thank you. If you want to stick around, I'll try to troubleshoot this, but I'm gonna save it. The GPU version of this will come up for a later webinar. Just barely got that going last night. It's actually not that hard to, I mean, it really doesn't take any change, but I was able to show it running on a GPU. And so the ramp up of doing remote functions with parallel processing was quite dramatically different. I was hoping to be able to show that, but I don't, something died on my Jupyter under the hood. So I'm going to save that for later. All right, let me shut this thing down if I know how. Stop share. Boom. Okay, great. Okay, thanks for bearing with us. Looks like we have one more question come up. Okay, great. So would it be possible to get the link to the code repo? Yeah, actually, all the notebooks, all of that, and directions about how to get set up, they're all there. One thing that we're adding is an FAQ because based off of the last session, but also this one, and some people adding some GitHub issues and whatnot, we have some more info about different edge cases you might catch. So we'll add an FAQ, but most of what you need to get going should be there in the repo. And Louis, I agree. We need futures for live demo results. Yes, yeah, I wish I could have wrapped that in some sort of semantic guarantees. Absolutely. Let me show one last part. Let's see, we have here Ray design patterns. I mentioned a shared document. There's a much more advanced material. There's a really great article by Ben Lorca and Jan Stojka that talk about putting all of this together. Sorry, I'm not sharing. Let me go back. Share screen. Boom. Okay. Hopefully this will make more sense. So Ray design patterns, that's linked in the slides. There's a great article called Infinite Laptop if you want to see more of a sense of how this is all put together. What can be done with multi-cloud once you're using these kind of design patterns in Ray. There's a great demo of this that Edward Oakes did at the last Ray Summit. And also, speaking of Ray Summit, that's coming up. The CFP is out. Registrations, I believe, are open, but it'll be coming out June 22nd through June 24th, and it will be online. I'll be teaching one of the tutorials, I think, the first half of the day, and hope to see you all there. Also, in terms of Ray Project, there's a forum, definitely the various GitHub repos are associated. There's Twitter, good place, good resource to ask questions. But our Slack channel and our forum are really some of the best places to go in and get help from developers and other people in the community. So I highly recommend that. And if you want to get a hold of me, here's my homepage, my Twitter handle. Let's connect up on LinkedIn, etc. Thank you very much. That's all I got. I'll stick around for questions. Let me see if there's anything else that's come up. Oh yeah, great. Okay, Peter had a question. Can you give guidance on working with data frames in Ray, Modin, Dask, and Pandas? Yeah, very interesting question. So something. Now I mentioned a mini book about this that's in progress. When you look at the languages, Python, C++, Java, Scala, etc. But when you look at the languages, there's a few missing parts. There's nothing really native that describes a data frame. That's something that's evolved separately. And so since 2009, Wes McKinney came out with Pandas, and this notion of data frames really took off. It was what all of us used to do ad hoc otherwise. So creating a data frame has just become this kind of lingua franca for a unit of work inside of a pipeline. And when you're trying to distill your data down from a lot of different sources, run some Spark or whatever to do your joins, you can use data frames there, right? And then once you've got a data frame, this can also be operated on in things like Dask. So Ray comes into the picture in a few different ways. There is something called Modin, which is a way of parallelizing pandas on Ray. And so that's something, I believe it has Intel sponsorship. There's a kind of Python workflow manager called Dask. At a relatively high level, some real smarts in it, as well as like managing parallelism across the stages. And you can run Dask on Ray. And also Dask has become a really good kind of pattern to leverage. It's really been enhanced by NVIDIA for, say, running on GPUs. And the idea is that pandas data frames are really this like central unit of work. Once you distill your data down into a more compact, dense form, then you can start to apply a lot of parallelism to it. On the one hand, it's a unit of work that's flowing through a pipeline, whether that pipeline is scikit-learn or whether it's a Dask pipeline or whatever. But if you use the idioms of the pipeline, then you have a lot better, there's a lot better opportunities for guarantees of the underlying subsystems to parallelize it. So Dask can do smart things if you're using the idioms correctly. Scikit-learn can do smart things if you use the pipeline's idiom correctly. And when you talk with like the scikit-learn people, they will go off about the horror stories they have of people writing tons of custom code to sort of create pipelines on the fly when they could just use pipelines and it would be a lot more effective. So this is an argument for using very idiomatic Python or whatever language you're in so that the underlying subsystems can pick up on the design patterns and parallelize it well. And so that's part of the guidance is learn to do idiomatic Python, learn to be using, Louis, you can definitely call me out on this, but use comprehensions appropriately. And if you dig into Stack Overflow, talking about how to work efficiently in Python, you'll see a lot of things about if you need to build a data frame, build it from a dictionary, a list comprehension, a list of dictionaries. Do not build it incrementally. So there's a lot of best practices that are just sort of floating around there of idiomatic Python, but they allow these underlying tools to work properly. And Python is very forgiving. So if you don't do the idiomatic approach, your code will still run. It might run 3 orders of magnitude slower, but it'll still run. So that's kind of the trade-off there. Now, having said that, once you've got dense data in a data frame, it's interesting, are you going to apply functions, like actually use pandas to apply a function within the data frame, and then there's some opportunity to run things in parallel? Yes, generally. There's something, in terms of Modin, it's a pretty close drop-in replacement. Dask has a lot of nuances and different things that can go on there. I'm not really going to speak about that in this tutorial. It's way out of scope. There's certainly this idea of using CUDF as another kind of drop-in replacement that is GPU aware and highly optimized version of data frames by NVIDIA. And then downstream, depending on what you're doing with scikit-learn or NetworkX or Spacey or whatever, if you have used the right kind of data frame to start out with, that can be propagated down through the different stages for more advanced processing. So, you could write a book on this, and in fact, we are writing a mini book on this. Hopefully, it'll be out within the next 3 to 4 weeks, actually, maybe a little bit later. But definitely, I would love to follow up on that with a different version of this that goes into more exploration of, again, this kind of like the implications of hardware evolving very rapidly, more rapidly than software is evolving, certainly more rapidly than the languages. And these notions of like data frames and graphs and pipelines that aren't native in the language, but are being used in language. And you have to really stick toward the idiomatic uses of them if you have any hope of leveraging the underlying subsystems. Anonymous said, thanks for GitHub link. Can you please share the link to this presentation? Yeah, the link to the presentation is in GitHub repo. Thank you. That's a great question. But there's a lot of links in the slides, and it's all in the GitHub repo. Let me see what else came up. Let's see what else I may have missed. Chat. Great, and we'll be reposting, Sophia mentioned also, we'll be reposting the video from today. So that'll be on the YouTube channel. And Ray Summit is coming up. I'll put in another plug. You've got the link for the forum. We'd love to get feedback. You've got the sorry, I'll stop share. You've got the repo, and certainly let's talk further there. If there's any changes you'd like to see or questions you have about particular code, the GitHub issues are a good place, but also the Ray forums are really good. And having said that, I'm only a half hour over. My apologies. I hope that this was helpful. Thank you very much. All right. One question, Sophia, should I end the recording? Will I end the whole session if I do? Okay, great. Bye, everybody. Thank you very much. See you online.